protons and neutrons are just made up of up and down quarks. But nature somehow gives us not one, but not two, but three families of these particles. So again, not one family, but two and three. And this is one of these great mysteries of nature. We don't seem to see 4 or 5. There weren't 2. There happen to be 3 and only 3 families. But we continue to look because there might be other particles out here that are extremely heavy that we haven't seen yet. On the other side of the diagram are standard force carriers like the photon, the gluon, and the W and Z bosons. These are the particles that mediate the forces like the electromagnetic force and the strong force. And then finally, after the discovery, we could fill in the last remaining bit of the standard model table, which is the discovery of the Higgs boson. So somehow this is this mysterious particle that talks to all of these different other particles and gives them their masses. So it looks like we have a very complete picture, so we should be shutting down our experiment and going and doing other things. But it turns out that we actually have a lot of new questions that we still want answers to. So one of the big questions is, why do these particles have the masses that they do? Because these particles can have mass due to the Higgs, but it doesn't explain why the electron is so light and the tau is so heavy, or why the top quark is as heavy as a caffeine molecule. These things are really all over the map, and then the neutrinos are incredibly light. The gluon is exactly massless, the photon is exactly massless, these guys are heavy, the Higgs is pretty heavy. So the Higgs allows there to be mass, but it does not explain why the particles have the masses that they do, and we're not going to be happy until we can understand or predict why the particles have the masses that they do. So that's still a open question. We discovered a Higgs particle, and it's possible that there are other Higgs particles as well. And in fact, with my graduate student and postdoc, I'm searching right now for additional Higgs bosons that would be telling of some deeper forces of nature, deeper understanding. This question about the 3 families of particles we still don't understand. We have these different forces. They all look sort of different at low energy, but as you go to higher energy, they start to unify, as I was explaining earlier. So maybe they all unify at some very high scale, including perhaps gravity, and I have a picture to show you about that. And then finally, we have other remaining questions that are somehow tied in with cosmology and astrophysics. And there's this incredible connection between the smallest particles in the universe and the largest structures in the universe, and which are studied by cosmology. So why is there this matter-antimatter asymmetry? Where is the universe's antimatter? What are the sources of dark matter and dark energy in the universe? So the astronomers and astrophysicists and cosmologists make these incredible measurements that show us that on a very large scale, something fundamental is missing. And we believe that we might have particle explanations for at least some of them, but we have to discover the particles, and we haven't seen them yet. The Higgs boson is not the answer to these questions. So there's actually an enormous amount that's still left to be studied, and that's what we're working on. So here's kind of a fascinating energy scale. It's like a temperature plot. So we're going up by an incredible 30 orders of magnitude. So every one of these, if you can't read it, is another factor of 1,000. And at very low energies, we have these forces, the electromagnetic, weak, strong, gravitation. And these all sort of evolve, they change as we go to higher and higher energy. And this is that unification of the electroweak force. And the Higgs boson is implicated here. But it's possible that at very high energies, we might be able to unify with a strong nuclear force. It's called grand unification. Going up even higher, you could bring in the Planck scale and perhaps tie in gravitation. And then it's just a short hop to get to Big Bang. So we're sort of here, and our theories are thinking about the big questions up here. But there's a really funny part to this, which is this little energy scale, which we call the terascale, should not be stable. So theoretically, there's a problem because it should be sliding. That Higgs boson should not be 125 GeV. It should either get really heavy or it should be really light. And this is a funny little point that seems to be fixed in energy, and we don't really understand. Maybe there's something fine-tuned about the way all of the particles and all of the forces come together. And the question is this a natural phenomenon that we've discovered the Higgs and we have this electroweak scale? And so a lot of the theorists that we work with spend a lot of time talking about naturalness, and if things are natural and things are not natural, and whether or not it's important to be natural. Well, is this natural? Okay, so these are my postdoc and graduate student, Rachel and Francesca, working at the pixel detector, but this was a nice picture to show that they're also working on a search for new exotic Higgs bosons. And this is an example where the protons would collide. This is a little schematic. The Higgs would be shown here, but the Higgs would decay to lighter Higgs bosons that we have not seen yet, and we would search for them by looking at tau leptons. And so they're doing a great job. We're almost done with this, and we'll be able to present the results in conferences. Really exciting is that starting this year, the energy of the LHC has doubled. And as we double the energy, the probability of discovering heavy particles goes way up, way up. So nature may have some particles right around the corner for us that we haven't seen yet because the energy of the collider was not sufficient. So we're very excited about this. And then in the future, we're already talking about what we call the high luminosity LHC. And so here's our haystack of enormous numbers of particles in one given collision. And what we're trying to do in this era, which won't start for a few years, is to find new particles in that haystack. And so some buzzwords are supersymmetry, exotic Higgs particles, black holes, extra dimensions. I don't really have time to go into these, but I'd be happy to answer questions if you have them. And this detector will be in a very high radiation environment. And so a lot of the work that we're doing is learning how to build detectors that will withstand the radiation damage that is going to be present at that, in that era. So this is kind of down the road. The detector will look something like this. We'll have a new tracker, a new calorimeter, a new trigger. And I wanted to make the point that if you're in 6th grade, any of you in 6th grade? Younger, older? No 6th graders? No. You'll be in 6th grade soon.
8th grader.
All right, 8th grade. You can analyze the first data from the high luminosity LHC as a college undergraduate. So yeah, it's going to be a few years before we get the data. But by the time you're there, we'll be ready for you, and we'll hand you some really exciting data to analyze. And I just want to plug UC Davis again, that in our physics department, we often have our undergraduate physics majors do research with us. So no longer do people wait till they get to graduate school. We have an enormous number of excellent undergrads that love doing research with us, and so they can analyze the data just as well as grad students. And so that's all I have for you. Here's some conclusions. Particle physics is an amazing combination of theory and experiment, and UC Davis is heavily involved in both parts of this. And so I decided to take these two pictures. So we have, who do we have here? Albert Einstein. And who do we have here? Not quite as famous, but pretty famous. So we have a theorist and an experimentalist. You can tell the experimentalist because he's in a bunny suit. He's working in a clean room. This is Sam Ting, discoverer of the J boson, Nobel Prize winner. And he's the leader of a very important, the very important science experiment on the International Space Station. So physics makes its leaps and bounds and its discoveries and innovations by the interplay between theorist and experiment. And at UC Davis, we work on both. The discovery of the Higgs was 50 years in the making and involved many, many theorists and thousands of experimenters. The Higgs discovery raises more questions than it answers. In 2015 and beyond, we're going to have higher beam energy and a lot more data to analyze, so we're hoping to see more excitement. And so let's find out what nature has in store. Thank you very much. If we have time for a few questions, I'd be happy to answer anything. Yes?
What exactly is the Higgs boson? Like an atom or an energy source?
So we understand that along with some of these other quantum particles, there is a wave, there's a field called the Higgs field, and disturbances in that Higgs field gives rise to the Higgs boson itself. So we have both a particle and a field. And this is a particle that's not like the atom is a different kind of a particle, and in fact, the atom is made up of others. But if we want to compare it to an electron or a quark, the Higgs is another particle, and it's not made up of those.
Part of the atom.
So the particles in the atom all talk to the Higgs. The Higgs is there, and the Higgs is what's giving them their masses. So you're right. Yes?
And this kind of industrial vector that you have to analyze what is happening, where is actually where you are detecting the energy electrical power, what is property are you looking at? The temperature? What is the specific physics
Right.
that you are kind of looking at?
Very good question. So let me bring up the. Okay, so here is one bunch crossing, and what looks like it happened is that two gluons fused and produced a Higgs boson. The Higgs boson decayed to two photons, and the other constituents in the event gave us all of these other particles. So these particles can be electrons, they can be muons, they can be a whole host of things. We measure the directions of the charged particles because a charged particle in a magnetic solenoid will give us a helical trajectory. And so what we do is, since the detector is so big and has all of these different little measurement sensors, we can map out exactly where all of the particles went. Which ones? The gold? The photons are these guys here. So let me explain the photons for a second, because that's the important part of this one. So what we have is a scintillator made out of a very heavy crystal called lead tungstate. And when the photon goes into that crystal, and each crystal is about size like this, like a small ruler, and the photon will deposit all of its energy and produce scintillation light. And that light will get read out by a little electronic detector, and we'll get a little blip that we combine with all of the other data in the event. So it depends on the particle type, the photons. So this long red box is just representing how much energy went into that direction. And that's what we think this one is. So nature doesn't tell us that this was a Higgs, but this looks a lot like the Higgs. And what we can do is we can take the energy of this guy and add it to the energy of this guy. So we have to measure the directions and the energies and the momentum. Then we can correctly calculate the mass of the particle that must have decayed into that pair. And what we find is that this is very consistent with 125 GeV new particle. And we ended up with a few hundred of these events, and we were able to say that they were definitely not background. We had one of the things that was very important was to build an electromagnetic calorimeter that was fine enough resolution that we could measure these things very precisely. That was a very important aspect of the design of the experiment.
If I understood correctly, basically you have a special crystal with like a photodiode.
Yeah, the photodiodes, exactly. Okay, and inside these are measured with silicon strip and silicon pixel detectors. Other questions? Yeah.
Yeah, I've noticed your field was 3.8 Tesla. Is that correct?
Yes.
So how do you turn it on and off? Yeah, I've noticed that you mentioned that because isn't it like a superconducting magnet?
It's a superconducting magnet, so it's at liquid helium temperature.
Okay.
And it takes something like 9,000 amps of current. And it's not something you do without thinking about it very carefully. There's a lot of safety systems. It's cryogenic, and there's a lot of electricity going through there. It was a huge R&D effort, and it uses very exotic metals for the structure. The collider itself also has superconducting magnets. They're just not solenoids. So the solenoid is the right shape for us when we're actually measuring the particles. We have dipole magnets, for example, to bend the protons into the ring of the giant Large Hadron Collider.
So once it's ramped up, does it stay at that field? Do you ever shut it down?
We shut it down as little as rarely as we can get away with, because there's always a little danger of doing that, because things can move when you turn the magnet on and off because of the magnetic force. So we do it a couple times a year. I'll show it to you later. Yes.
Speaking of things moving, I remember hearing when you actually put the field through all that iron that's there in the detector, that there's so much, the magnetic force is so strong, and the field is so strong, that the iron actually expands significantly. It's huge. So do you remember how much it's something like a foot?
It may well be 30 centimeters. Yeah. This is the world's largest superconducting solenoid. It's something like 9 gigajoules of stored energy. There's a whole Guinness Book of World Records page now for the experiments at CERN. Really impressive. Other questions? Yeah.
Yeah, we can accelerate any charged particle, but it seems like mostly you do protons. Can you do other things like electrons?
Okay, so so the very good question is, we're colliding protons. Can we also accelerate electrons and other charged particles? And the answer is yes. So we've used other accelerators in the past that collide electrons, for example. You could try to collide muons, but the problem is that the muon itself is unstable. And so you're trying to have a lot of particles in the beam, but they keep decaying. It makes it very hard to do. But on the other hand, people do consider making a muon collider. If you had enough muons in there, you could actually compensate for the fact that some of them decay. Yeah.
Why do you choose protons?
So why do we choose protons is the protons are by far the easiest particles to accelerate to extremely high energies. So electrons have a lot of benefits. Electron colliders have a lot of benefits, but high energy is not one of them. And the reason for that is that as we try to accelerate electrons to very, very high energies, they radiate off that energy. It's called synchrotron radiation. And protons, since they're much heavier, 2,000 times heavier, they do not undergo that. That's not an issue. So just from a technical standpoint, it's very much easier to collide protons at high energy. Other questions? Yeah.
So maybe you covered this earlier, but I came in and apologize. So is the Higgs then part of everyday matter, and we can only observe it with these high energy collisions, or is it just a rare thing that only happens that you can only have when you have these collisions?
Great. So the Higgs, and this is a very good question as a follow-up to a previous question. So the Higgs field is always there, and the particles are all going through the Higgs field and acquiring their mass. It's very hard to create a Higgs particle on purpose in the middle of your detector the way we do it. And so that's the point. The Higgs is, the field is there, it's the interaction that we need, but if we want to make a Higgs now, then that's a very rare occurrence. Okay, and it has to decay into those two photons, and the detector has to be ready to go, and so on. So that's why it's so hard to do experimentally. Yeah.
How fast are you accelerating the protons?
We're accelerating the protons almost to the speed of light. So you can't get particles that have mass to the speed of light. I did the calculation. The protons are going 7 miles an hour slower than light in our experiment. So they're 12 miles an hour faster than they were the previous year. Yeah.
You mentioned you might create a Higgs. How quickly does it decay when you do?
It decays incredibly fast. So there's no chance that we'll ever have the Higgs particle itself go through our detector. So something like a trillionth of a second. And it turns out other heavy particles in particle physics also decay very quickly, like some of the heavy quarks. But anyway, the Higgs decay is extremely fast.
Let's thank Professor Chertok again for a great talk.